Right, so I'm going to talk about this, and this is based on work with Gabriel, who's here, and a student who's using this for his PhD thesis, Davide Polini. So first, why count BPS black holes? What is it all about? So primarily the idea is counting black holes is a very vital area of research in string theory or in any theory of quantum gravity. And that's partly because black holes have entropy. They have wonderful thermodynamic properties. They have huge entropy even at zero temperature. So one of the testing grounds for quantum gravity is if you have a putative theory of quantum gravity, you have to be able to give a statistical mechanics description of the degeneracy of microstates, which gives rise to this entropy. So it's just like in thermodynamics where you have a macroscopic law, gas laws, and if you have an atomic theory, then you should be able to use the atomic theory to come up with a statistical mechanics description of degeneracy. So in principle, you should be able to come up with, so the quantum theory, so if there's a quantum theory of gravity you want to test, it should be able to produce a description, should be able to write down a partition function of sorts, where given say a black hole, which is parameterized by some, say, charges qi, you should be able to write down a partition function in terms of, which is a generating function for the degeneracy of this black hole as a function of qi with some chemical potentials phi I. This is a very heuristic statement. Now, if you can do this, then of course, asymptotically, at large charge, this must correspond to the thermodynamic entropy, the macroscopic black hole entropy, which is this one. So the black hole entropy has a very interesting feature. This is an expansion of the black hole entropy in terms of the area of the black hole. So the leading order entropy is holographic, so it is proportional to the area. So that's the Bekenstein-Hawking term. And then there are log area terms, and there's an expansion in areas with non-perturbative terms. Each of these terms, so the area is basically, for the black holes we'll be considering, which are called extremal black holes, the entropy is purely a function of the parameters of the black hole, which are not temperature. It will be just charges. The area will be a function only of the charges. And so you demand that at large charge, the asymptotic growth of this will be exactly like e raised to area by 4. That's one of the checks of the theory. Also, the theory you're looking at, the gravity theory you're looking at has certain symmetries. Then under those symmetries, the entropy of a system should not change. And so you demand that the partition function should change, which should transform covariantly in such a way that this d micro does not change at all. So those are some of the tests that you need. Okay. So string theory, turns out, which is a putative theory of quantum gravity, has actually had some successes in coming up with some microscopic descriptions of degeneracies. So in particular, for a very particular class of black holes which are dyonic, so that means they have electric and magnetic. So these are in theories which have gravity coupled to both abelian gauge fields with some neutral scalar fields. So a black hole can basically have electric and magnetic charge. It can be charged with both electric and magnetic charge with respect to the abelian gauge fields. So black holes which are both electric and magnetic charges are called dyonic black holes. They're BPS because they annihilate some of the supersymmetries of theory, but they're basically extremal. We are counting a class of extremal dyonic black holes in theories with very large supersymmetries. These are four-dimensional theories of gravity, where the supersymmetry constrains the matter content that can be coupled to the gravity. And so the partition function Z for certain classes turns out to be modular. This is a Jacobi form, and this is a Siegel modular form, which is a modular object for genus 2, which we'll come to in a moment. So the common theme that we find when we try to count black holes, extremal black holes in string theory, is that the partition functions tend to be kind of modular objects. So we'll come to why in a moment. So the black holes, the typical gravity theory we're considering, and this one will consider a gravity theory with lesser supersymmetries than the one we're looking at. So it's less of a toy model. Is n equals to 2, which means it's a four-dimensional theory with 8 supersymmetries. It's basically a theory of gravity. It's got some U1 gauge fields and got some complex scalars yi. So the black holes can have charges, electric and magnetic, which I call qi and pi. Now, because of the supersymmetry, the couplings of the matter content of the gravity are completely encoded, can be completely encoded in one function, one holomorphic function of the scalar fields, which is f. We'll call this f. Now, because the black holes are BPS, it basically means they're extremal, which means they're zero temperature, and they all have one common property. Extremal black holes always have a near horizon geometry, which is ADS2. So this is and more importantly, if you look at because of the coupling of the matter fields to gravity, the scalar fields see an effective potential in the black hole background. So they flow in from infinity and they go all the way to the black hole horizon. There's a potential that governs the flow. And the potential is such that at the horizon, the values of the scalar fields is completely fixed by the charges of the black hole. In other words, it's independent of the asymptotic value it took from. In other words, the black hole's horizon, near horizon geometry, is a classical attractor in the space of the yi's, scalar fields. So the attractor equations, this allows us to write the attractor equations. That means the endpoint of the flow as this much. Now it turns out that the attractor equations are not expressed in terms of yi's are complex scalars, but somehow the convenient way to write down the attractor equations is to look at the degrees of freedom, is to categorize the degrees of freedom not as real and imaginary parts of y, but as imaginary parts of yi and imaginary parts of fi, which are derivatives of this potential f with respect to the yi. So these are the attractor equations. If you solve these equations, you know the value of the scalar fields yi at the horizon completely fixed in terms of the charges. Now the ADS2 is fixed in terms, so we will consider, now remember when we are looking at the partition function, we had some charges and we had a chemical potential. So we can choose an ensemble where the magnetic fields, magnetic charges are fixed. So we are only looking at various configurations with different electric charges. So this is called the canonical ensemble. While if you have both electric and magnetic charges varying, then it's called the grand canonical ensemble in this setup. So because we have fixed the magnetic charges, this equation immediately tells you can rewrite the yi very trivially like this. There's an undetermined real part here, phi I, and you can determine the real part phi I as an extremization principle of this particular expression. So you take this expression, this is called the classical entropy function. This is the f, which is a coupling function here. Replace the yi with phi I plus ipi by 2, that's a prescription. Then take the imaginary part and take a Legendre transform. If you extremize this, then you can solve for the phi i's completely in terms of qi's. And so you have determined the yi's totally in terms of q's and p's. And of course, you can determine the fi's too, obviously, in terms of this. So this is what is called, this is the semi-classical entropy of the black hole. By semi-classical entropy of the black hole, it means that it captures, so in the expression you saw, it can capture area by force, it can capture the perturbative 1 over area corrections, it can't capture the non-perturbative corrections or non-local terms like log area. So the actual, I should have written down more precisely, this is called the Wald entropy. So it captures all the perturbative corrections to the area and the area itself. The full, but we of course would like the full answer, the full S, so to say. And so based on this, there's a conjecture which is called the quantum entropy function conjecture. And the conjecture is the following. Because the near horizon geometry of the black hole is an attractor point, all the matter content in the near horizon geometry is fixed in terms of the charge of the black hole. And so therefore, the number of the microscopic degrees of freedom that make up the degeneracy of the black hole should basically depend only on the near horizon geometry. So Ashok Sen conjectured that the correct partition function was basically a path integral over various field configurations in the ADS2 near horizon geometry. If this partition function existed as a well-regulated object, then this would basically give rise to the degeneracy of the corresponding black hole. Now, this is obviously a very complex statement, and this is a statement about doing a path integral in quantum gravity in some ADS2 background, which we don't know quite how to do. But in the very specific case of BPS black holes with enhanced supersymmetries in an n equals to 2 case, you can actually use localization, equivariant localization techniques to actually handle this, make this integral tractable. And in fact, that well-regulated path integral reduces to essentially a bosonic integral, a finite dimensional integral over the fields phi I. So these are the fields phi I. And it's simply a bosonic manifold. And so this basically looks like a path integral where this is like the action. So this is, you can think of this as the quantum version of this particular statement. And of course, the saddle point contribution comes from the extremization of this thingy. So this is a conjecture. Now, to use this, now because the path integral is supposed to be over ADS2, ADS2 has an isometry, which is the SL2R isometry. You would not be surprised to find, you would expect naturally that the partition function transforms well, is well behaved under an SL2 transformation. And that's why you would expect it to be essentially a modular object. So before we do that, and that's one of the reasons why you expect that's one of the reasons why you find in the previous slide, in all the other examples, you find that there are modular forms appearing. So because there is this consistent recurring theme of modular forms, it might be good to take a digression for a moment. So the simplest modular forms we're looking at is SL2, those under SL2. SL2 is the large diffeomorphism group of a torus. I'm looking at the integral SL2, so that's ABCD with AD minus BC is 1. The large diffeomorphism group of the torus has a period as a single complex period, which is tau, given by tau 1 plus I tau 2. It's defined, modular forms are defined on the fundamental half plane, upper half plane of this thingy, and a modular form of weight k satisfies this transformation property. So in other words, an SL2 group SL2 operation can act on the period number of the torus, and the corresponding change of the modular form is this way. And a modular form weight k transforms like this. If the modular form, now one of the generators of this transformation is tau goes to tau plus 1. Under tau goes to tau plus 1, as you can see, f tau plus 1 simply goes to f tau, so it's periodic. And therefore, it has an integral decomposition. So you can write down the f tau as a generator of coefficients an with some chemical potential determined by the fundamental period, by the period of the large diffeomorphism group. So that's e raised to pi tau. Now you can look at various forms of this modular forms. If the n, so the n of course terminates at some value. Now if the n terminates at some negative value, then it's called a weakly holomorphic form. And then the asymptotic growth of the coefficients is exponential. While, for example, if the n terminates at, if the an is basically 0 for all n less than or equal to 0, then it goes like a polynomial. It goes like a power law. Now, the exponential one is the one that is most interesting to us because the entropy of the black hole that we have, this is the area, for example, goes like quadratically in terms of charges for most of the black holes we'll look at, which means that the degeneracy, which is exponential of this, goes like exponential of the parameters, exponential of quadratic of charges. So we're always interested in modular forms where the coefficients have an asymptotic growth that is exponential. Those are the ones that are important for us. Now we can generalize this and go to the Jacobi forms. These are modular forms. We can go to the Jacobi forms, which are functions of two variables, the tau, and there's a complex variable z. And because it has got two variables, it has obviously got two indices. One is the weight k under normal transformation, under the modular transformation, and there's an index m that talks to the z. And this is the transformation property. It has, apart from the normal modular transformation, there's a spectral shift, an elliptic shift, which basically is governed by, there's an m here, and the weight and the transformation is governed by the index m. Because of this particular spectral shift, you can write down the coefficients as simply a function of 4nm minus l squared. So ordinarily they should just be functions of n and l, but you can write them down as 4nm minus l squared, q raised to 1, y raised to l. So one of the modular forms that we looked at, so for n equals to 8, one of the partition functions was precisely a Jacobi form divided by a modular form, interestingly. And this, of course, also gives rise to, and you can find out so there is an entire series of, so you can, given a Jacobi form like this, you can basically figure out the asymptotic growth of C using a Rademacher expansion, and it turns out for this one too, it's exponential. The forms that we will be interested in, mostly, will be Siegel modular forms. Now, Siegel modular forms are generalizations of this to higher genus. So genus 1 is obviously for a torus, and it has got one complex parameter. Genus 2 has the period vector. The period is basically a matrix, and it consists of 3 period complex numbers. And the corresponding large diffeomorphism group is SP4. So the period matrix in this case, which we call omega, has 3 complex numbers, and these are 2 cross 2 matrices. Each of them is a 2 cross 2 matrix. This is the operation where AD transpose minus BC transpose is one identity. And now, just like the modular forms, you can define the Siegel form, which is a modular form for genus 2 with a weight k as a function of omega. So the way the SP4 acts on omega is a omega plus b by c omega plus t, and this is the determinant of phi k omega. So that's a Siegel modular form. Now Siegel modular forms, it turns out, appear as partition functions of n equal to 4 theories. These are far more involved and they have a whole structure to themselves. So interestingly, for n equal to 4 theory, the partition function, so it is actually instructive because we're going to use a Siegel modular form for n equals to 2's. The Siegel forms can be written down as generators of integers numbers n, m, l. There are 3 period vectors. There are 3 period numbers. So each period number is like a chemical potential. So it's basically q raised to m, p raised to m, p raised to m, q raised to n, y raised to l, where p looks like e raised to 2 pi I rho, q looks like e raised to 2 pi I sigma, and y looks like e raised to 2 pi of v. Now, so suppose somebody gave you this as a generating function for your degeneracies and you wanted to find out the degeneracy of this. Of course, you do a inverse transform. And so you would have to basically work out minus L divided by phi k. And you would have to work out how to solve this integral with a specific contour that's defined. Now, we will be concentrating specifically on a very special class of Siegel modular forms. The Siegel modular forms that we're looking at are those that can be actually built up from Jacobi forms, from genus 1 forms. So there is a special operation given a Jacobi form of weight k and index 1, one can operate on it by an operator, by a Hecke operator of index m called Tm, which will convert it into a Jacobi form of the same weight but index m. And then one can take a generating function Pm Tm phi k1. Remember, the P is a completely different chemical potential. And this will give you a function of 3 variables, of course, rho, sigma, v. And it turns out that if you therefore start from a Jacobi form, which is a genus 1 object, and you apply to it the Hecke lift, and then you look at the generating functions of Hecke lifts, then that becomes a Siegel modular form. So this is called the arithmetic lift or the mass lift. And we'll be looking at Siegel forms that can be obtained from genus 1 forms, specifically like this. So for these forms, just these forms, and in fact, we'll be looking at very special kinds of phi k1s. So our phi k1s will always be of the form theta, a very special Jacobi form, times some modular form, some modular object. So this is our Jacobi form. So if you take a Jacobi form that's of the form theta 1 square by eta is 6 fk tau, but these are 2 specialist forms. Fk is an arbitrary modular form of weight k, by the by. Then whatever form you get by constructing the Hecke lift has very special properties in terms of polar structures. As you can see, when you want to count the degeneracy formula, you are doing an integral, and therefore it's important to know the pole structure of this thingy, and it's also important to know the residue behavior of this function of the poles. So for these particular objects which come from phi k1, there's a well-defined residue behavior, which we'll come to in a moment, and that is what allows us to basically extract the asymptotic growth of coefficients for D, and then compare that to degeneracy formula. Okay. What am I supposed to do with this? Sorry.
Ooh, it's got me away.
Eventually. Yes, right. Good. Sorry. Okay, so back to where we were at. We still want to compute this degeneracy formula, and there is a path integral where there's an integral defined over some bosonic fields. So we have to know this, and we have to basically know the measure, and then we have to specify a contour, if at all we are going to try doing this. So now, for most theories, it's very hard to obtain the function f. to all orders. But we're going to look at a very specific theory, which is a four-dimensional n equals to STU model. So this is a four-dimensional theory, string theory, which has four complex fields, y0, y1, y2, y3, which we parameterize as y0, s, t, and u. It has an exact duality symmetry. So what does that mean? It means that these are operations you can do on the s, t, and u scalars, which will keep the entropy and therefore the degeneracy invariant. So the gamma 02 is basically a subgroup of SL2, and it's a subgroup of SL2 A, B, C, D with C equal to 0 mod 2. Is that? So if I say gamma 02 S, think of the S as a tau, and then you basically think of this as A tau plus B by C tau plus D. So you can do three different operations on S, T, and U, and it doesn't change the degeneracy. Also, there's a triality symmetry, which means if you flip S, T, and U, nothing happens to the entropy. So these are symmetries of the theory. Because of symmetry, so these symmetries are exact, and therefore, you can use the symmetries to constrain the form of F. And it turns out that you can constrain them completely so that you can write down the exact F function for this particular theory. And the F function for this theory can be written down as an F0, which is a classical F0 plus 2i omega, which is this plus this. The 2i omega is an infinite set of gravitational coupling functions. So it's really hard to actually write down the F for any generic n equals 2 model precisely because there are infinite number of terms. But because of the beautiful exact duality symmetry of this theory, the constraint is so high, it's so tight that you can actually end up getting all these functions. So this was done by Gabriel, Davide, and Sapna Mohapatra in a paper that came out very recently, although it is still the prequel to this talk. And it turns out that what they showed was they managed to find out the exact omega. They managed to find out all the coupling functions of the theory, where omega 1 and omega n plus 1 are all well defined, and they're all defined in terms of modular objects. So theta 2 is a Jacobi form. In fact, they're defined in terms of logs of Jacobi forms, which are not quite modular, actually. So now, because we have this system, so we have the action, so to say, it also turns out that because of symplectic invariance, so the yi's and the fi's also form a symplectic vector on which the symmetries operate. And because of symplectic invariance, you can constrain the measure factor too. So we actually have the measure as well as the f for those things. As it turns out, so now we look at these terms and we understand that, okay, what we want here, so now we want to basically evaluate the integral. So we've got the full f. We want to evaluate this integral. There are four phi's here because it's got four complex scalar fields. So it's phi 0, which corresponds to y0, and then phi 1, phi 2, phi 3, which corresponds to y1, y2, y3. So the way we do this is we basically fix two of those. We basically evaluate this at a very special point for simplicity. We take the t and the u to be fixed at the attractor values, which means we fix phi 2 and phi 3 at their attractor values. And then we simply think of it as a fluctuation. We simply think of it as an integral in phi 0 and phi 1. So once you compute that, so we basically fix it at attractor values. We look at fluctuations around the attractor values. We reduce it to a two-dimensional integral. And so we'll basically end up getting an effective two-dimensional integral here. And so the question is now, what does a two-dimensional integral look like? So when we do that, we get a two-dimensional integral. What we have done is we have reparameterized. So phi 2 and phi 3 are fixed at their attractor values. Phi 0 and phi 1, which corresponds to y0 and s, are being reparameterized in terms of two complex variables, in terms of tau and tau bar. And so you basically get an integral in terms of tau and tau bar and a very, very complicated function like this. So this is the answer, apparently. The w is the same as d. Sorry for the notation issues. You get a very complicated answer, which is like this. And now the question is, can we read off a modular structure from here? So to do that, our first guess is the following. We wanted to understand where do we end up getting, if you have a degeneracy formula that looks like the integral of some generating function, where do we get d tau 1, d tau 2 by tau 2 squared? So it turns out the answer lies here in the Siegel modular form. So given three numbers and given an integral omega and e raised to minus 2 pi I rho m plus sigma n plus yl. If you want to compute this integral, the first thing we notice is that because phi k is actually in a Siegel modular form of SP4Z, it has an infinite number of zeros. Some of the zeros are images of each other. So you identify the zeros, in fact. So there's a 3-parameter set of zeros. So it's a function, so the zeros, there's a 3-parameter set of zeros. You identify the zero which gives rise to the saddle point, which gives rise to a saddle point that is actually equal to the area by 4, because you demand that the saddle point answer should be, the leading order answer should always be area by 4. And then it turns out that the zero that does the job is this one. So this is a zero of phi k, which means that it has, and it is a double zero, which means that it has a double pole on this particular locus. Now I can do the following. I can actually do an SP4 transformation on the rho, sigma, and v variables, which keep the entire integrand invariant, and transform this particular zero to simply a v tilde in a new frame. And so in this particular frame, at this pole, phi k looks like v square fk rho and fk sigma, where fk was basically part of the Jacobi form that was used as a seed for the Hecke lift that produced this one, interestingly. So it turns out that this, if you can show this, so if you start with a Hecke lift of a mass lift of a particular Jacobi form, you find that at the leading order pole, it will always behave like this, fk rho times fk sigma, and it's a v square, it's a second order pole. So then you can completely eliminate this integral by looking at the residue. You've got two integrals d rho d sigma and this thingy, and so what you end up getting is the following, and you can parameterize the rho as a tau and the sigma as a minus tau bar on the contour of integration, and so what you will end up getting is d tau bar by tau 2 square e raised to area tau tau bar by 4 e raised to minus f tau and an additional term, which is k plus 3 plus area by 4 tau tau bar. So what do I mean by area by 4 tau tau bar? It means this is a function of the charges of m and l and a function of tau and tau bar, such that if you do the saddle point extremization, you will get the exact area by 4. It will be fixed in terms of the charges in such a way that you get area by 4. There's an extra factor here, which is k plus 3. This is a subleading term, by the way. This comes from the quadratic terms across the saddle point, k plus 3. So now you look at this one, and you find, interestingly, that this term, q square plus qp plus this thing, this is actually exactly the area by 4 term. If you extremize this, you would have gotten the area by 4, the Bekenstein area by 4 term. So this looks like a k plus 3 if k is 2. And so you conjecture that, right. And so you conjecture that this integral actually comes from a particular Siegel form, phi 2. Now, which Siegel form does it come from? To do that, you have to actually look at the expansion around here. And from the expansion around here, we know that the f had terms like log of theta 2 raised to 8, interestingly. So remember that if you have an arithmetic lift, you get terms like, this is e raised to minus log f, e raised to minus log f bar. You get terms like log f and log f bar, where f is basically the seed for the arithmetic lift in the exponent. And so this looks like this is that f. So we conjecture that the generating function for this degeneracy definitely includes a Siegel form 1 by phi 2, which is a function of rho sigma v, which comes as the Hecke lift of theta 2 raised to 8. This is your f. And if that happens, then you will basically end up getting the first terms as log theta 2 raised to 8, which works perfectly well. Okay, so that's taken care of. But now we have other terms. We have this whole series here. Now this is not Siegel. This is clearly not Siegel. Also, there's a log of y naught square, which is not Siegel. We know that because the Siegel has exactly 3 chemical potentials. Now, in the n equal to 4 case, this was all that was needed to basically get the degeneracy formula right. So the question is, what do we do with these things? So we'll have to analyze them. Now, it turns out that if you look at them carefully, they are very interesting modular objects. The omega n plus 1, because of duality, the omega n plus 1 term can be actually obtained starting from the omega 1 term, which is the log theta 2 raised to 8, by a series, by a recursive relation. But what is actually the log theta 2 raised to 8 term? So if we go there, we find that each omega n plus term, we find that the omega term can return as in terms of monomials of ions and ions. Now what are these things? These are modular forms of gamma 0, 2. Interestingly, now omega s is of course log theta 2 raised to 8. The first term here is the derivative of log theta 2 raised to 8. Now, given a modular form f, which behaves like a tau plus b by c tau plus d is equals to this, the derivative of this modular form is not modular. It doesn't transform like this. So, in fact, this one is a derivative of log of a theta function. Actually, it is not modular. In fact, it is precisely quasi-modular. So quasi-modular forms are forms that basically are well behaved under tau goes to tau plus 1, but not under tau goes to 1 by tau. So the SL2 group is generated by 2 operations. Tau goes to tau plus 1 and tau goes to minus 1 by tau, for example. Quasi-modular forms are well behaved under this, but not under this. Basically, they're not fully modular. And the famous example is the Eisenstein 2, which is, of course, the derivative of log of discriminant by d tau. The Eisenstein can be made modular by adding a non-holomorphic term. And this is a fully modular form. So this is called quasi-modular, by the way. And so the first term here, so there's this term. This is actually like the derivative of log of a theta. This is an Eisenstein of gamma 0, 2. This is called I1. We'll call it I1. Now, once you have the Eisenstein, you can generate, interestingly, modular objects from Eisenstein using a particular interesting technique. So starting with Eisenstein, you can develop a series. You can differentiate the Eisenstein again and add to it a constant times E2 square. And this will generate a modular form of weight 4. Then you can generate, using the Eisenstein, you can define a covariant derivative, which is a derivative that preserves modularity. So this is called the Serre derivative. And the Serre derivative is something where you differentiate with respect to tau, but you also multiply the weight of the object and E2 on a function. So the Serre derivative on a function fk will produce a modular form of weight k plus 2. It's kind of like a covariant derivative. So in this case, but the Serre derivative uses the Eisenstein. Now, because I1, which is this guy, is Eisenstein of gamma 0, 2, all the other ions you can generate starting from I1 by looking at the Serre derivative. Just like you have E2, you have an E4, and then you have higher E6s, which come as Serre derivatives. You can generate these things. So there is a pattern here. So everything else is expressed in terms of ion. The full omega is a series expansion which can be divided into various sectors, a monomial sector, a binomial sector, a trinomial sector, and so on and so forth. Now, the monomial sector has a very simple set of coefficients. It's 1 by n factorial. Now, remember, we are still trying to do pattern recognition. We still don't know how to group this into some modular object. We just know there's a series of some modular object. It doesn't come from the Siegel. So if you look at this pattern, one of the things that looks familiar to us is the following. One way of defining, there are 3 specific Jacobi forms, namely theta 2, theta 3, and theta 4. As you know, the Jacobi forms are a function of two variables, and three of the Jacobi forms, 2, 3, 4, are even in Z. And because they are even in Z, they satisfy an equation. They satisfy a heat equation, which is d of tau minus d square of Z square operating on theta tau Z equal to 0. So they lie in the kernel of this particular equation. And because of that, you can take this Jacobi forms and you can do a Z expansion based on this. So you can do a Z raised to 2n by 2n factorial, interestingly speaking, of, and there is a lambda tau raised to n. So this is like a Z expansion of the theta function. Now, you can now start with log of theta. This is true, by the way, for theta 2, of course, because theta 2 is even in Z. You can also do this for log of theta 2. Now, log of theta 2 does not lie in the kernel of this heat equation, by the way. But nevertheless, you can use the heat equation. It'll be a much more complicated equation, and you can figure out what is it that log of theta 2 looks like. Log of theta 2 can also be expanded in a certain series expansion. The problem is, you do get ions, by the way, there. You get ions very well, actually. So it looks almost correct. It looks wonderful. Like, oh, I'll be faster next time. Sorry. How much time do I have left? 9 minutes. 9 minutes. 9 minutes. Right, sorry. So this almost looks like it's an expansion of a log of a Jacobi form, except there's an n factorial out there, which of course kills it. So then you ask yourself, all right, so maybe this is not the right differential equation to look at. Maybe you should look at an equation. You should find the equation. One way of describing the theta function is to say, okay, this has got a certain weight and a certain index, but you can also say it lies in the kernel of this differential equation. So we asked ourselves, what was the differential equation that would generate this thing, primarily? And then, of course, so this were computed, and then Gabriel, Bernard, and Swapna also computed the alpha MNs. They haven't computed the trinomials, but the alpha MNs were computed again in the limit where t and u were fixed at very large values. So there were lots of terms that were ignored, so this is just an approximate result. This is an exact one, actually. So we have 1 by n factorial, we have alpha mn, and the question was, if this corresponded to some kind of a Jacobi form, where y naught, 1 by y naught basically felt like a z, then what was it? So we looked for whether we could find out a differential equation. It turns out that we conjectured, based on this result and the approximate alpha mn we have, so this is not the exact one primarily, that we have a differential equation. So we said, whatever the form is, whatever the Jacobi form is, which does this thingy, it basically satisfies this particular differential equation. It did generate, this differential equation does produce 1 by n factorial if you solve it recursively, order by order. It does produce 1 by n factorial. It does produce alpha mn's that we have computed, but it's approximate. And it also produces trinomial terms, which of course we have not checked. So this is an interesting way to basically figure out structure in the system. Also, we find that if you look at the term, so if you look at these terms, namely the I1s plus this term, the sigma, so you call it the sigmas, so the I1 plus sigma, they also satisfy under relation. Give me a second, sorry. So just to clarify, so now we say that the d tau d1 came basically from a three-dimensional integral over Siegel modular forms. So the conjecture is that WQP, the degeneracy, is actually captured by d rho d sigma dv, a Siegel modular form, and then there are the G's, which are the y0 dependent terms. So these are the ones that came from the ions. They are the ions and the ionms and so on and so forth. We don't have a closed form expansion for them yet because we haven't computed all of them correctly. But the algorithm that we're following is the following. There's a modular structure there. We identify the ions, we identify the ions and ioms, and we know the algorithm is, if you compute the coefficients, figure out the differential equation, and the differential equation should be basically to give you a closed form expansion, interestingly. The other structure that we found, which is rather nice in the system, is the cell derivative has under interpretation. It can be thought of as a Rankine-Cohen bracket. So if you take the derivative of a modular form, of course that is not modular, but there's a way in which you can take the product of two modular forms, the product of two derivatives. So if you have a modular form of weight k, and you combine it with the modular form of weight L in the following way. Minus L f dash k g L. Then this combination is actually a modular form of weight k plus L plus 2. Interestingly, it's totally modular. And this is actually a Rankine-Cohen bracket. You can think of this as a commutator, Fg of order 1. So it turns out that if you look at the series expansion, so if you look at the expansion, it had an I1, then it had an I2, an I3, an I4. I2 could be written as the Rankine-Cohen bracket of I1 with theta 2 raised to 8 by theta 2 raised to 8. I3 could be written as the Rankine-Cohen of I2 with the same thing. I4 could be written as the Rankine-Cohen of this with respect to the same thing. The Rankine-Cohen brackets obviously satisfy the Jacobi triple identity. So it looks like there is an algebraic structure to the system. So at the moment, the state of the art is the following. We basically managed to have an approximate description for the microscopic degeneracies of the n equals to 2 system. It's far more complicated than n equals to 8 and n equal to 4, which have only got Siegel modular forms. There is a lot of matter content here, partly because of the y0 term, which completely qualitatively distinguishes it from the other forms. Nevertheless, there is a very rich modular structure that emerges. There is a Siegel form that captures the n equals to 4 like part of it. And then there is, of course, a very suggestive set of structures which have to do with Rankine-Cohen brackets and with, for example, nonlinear PDEs that might allow us to basically eventually end up getting closed form expressions. And so the idea is eventually you can end up having a closed form expressions, and then you look at the symmetries of the closed form expressions, and that might give you indications about the non-perturbative structures theory. Thank you. I'm done.
Questions?
Yes. Hi.
So, if I remember right, at least in the n equals 4 case, I mean, because you also possess these EPS degeneracies and to undergo some sort of wall crossing.
Right. So, So, in n equals to 4 case, so think of that. So, it's basically this expression, just ignore the g's, okay? So, it's purely just a Siegel form. And then you say, there are pole structures there. Now, the leading order pole structure gives rise to the Bekenstein-Hawking, but there is a subleading pole which corresponds to the lines of Mandel stability. So, they are the ones across which you get jumps. So, in fact, one way to think about it is the following. You have a contour that is specified there. Now, in principle, there's a way in which the S-duality of the S-duality of the theory is embedded in the SP4. Okay? So now you can think of one of the SP4 operations that correspond to S-duality as operating on this integrand. The integrand remains the same, but the contour changes. And when the contour changes, it crosses a pole, and therefore it picks up a branch, and that's how we figure this. Now, the problem here is this is not the exact answer, first of all. So I'm not even trying, basically, at this point, to connect this to any kind of physically realizable ball crossing. But you're right. If I got an exact answer, then yes, so think about it.
More questions? If not, let's thank the speaker again.
Thank you.
Oh,